Got up this morning thinking it might be nice to brush off the old microphone headset and make some new trying to understand videos. This morning I'll be trying to understand Breaking the Lorentz Invariance by Stefano Quattrini. This is a preprint that he's put out on ResearchGate, and I've been discussing the issues with him and a lot of other people, but Valentin D made a legitimate point that I did not necessarily understand their argument. So I'm trying to find out whether there is any argument here to understand, and in particular, what I myself have missed. Let's begin then with the first setup. Twin clocks A and B, separated by a distance h, are at rest in inertial reference frame 0. Now this is weird. He's got inertial reference frame 0 out here in a box, and inertial reference frame 1 in here in another box, and v sub naught between them. So just to say that uh, this particular conceptualization of the situation where somehow inertial reference frame 1 can be represented as a box inside another box, inertial reference frame 0, it's a bit strange to me and may imply an incorrect understanding of what an inertial reference frame actually is. 2. A, comma, B are set in sync. T sub A minus T sub B equals 0 with a procedure A shoots a light wave to B. Okay, so there's more to this procedure. The procedure should be if this is x equals 0, or that's at coordinate x equals 0 in inertial reference frame 1, I guess, and x equals, say, r in inertial reference frame B. So let's call it r equals 0 and r equals r sub b. And then the time on when you shoot that light wave, you should set t sub b equals v c over r sub b. So the time that this clock is set to should be equal to the distance from that clock to there. And then if that works, and we'll call that for IRF1, since that seems to be more closely connected to what those clocks are, IRF1 must be the inertial reference frame where these two clocks are synchronized. Now, A, comma, B are accelerated with some proper acceleration g. Now, I don't know what that's talking about. If A and B are accelerated, then this is not and those two clocks are not in an inertial reference frame. However, it could be said that if A and B are doing their thing in this direction, or the two clocks are there and gravity is pulling those two things down. I imagine though what he's talking about right here is that they are going to accelerate in line so that the vector of acceleration is the same direction as the vector between them. That's, well, but I'm guessing, of course. By the way, what is a proper acceleration? Let's kind of go into this in a little bit of detail. It's something that I kind of need to review, and I know the Wikipedia article is horrible on this. So where I'm going to answer this question is probably the best place to find an answer for this question is in the Rindler coordinates from Wikipedia. So let's go in there. Coordinates of a hyperbolically accelerated reference frame. Okay, and here looks like the related math, x equals c squared t over alpha t. Okay, well this may not do exactly what I wanted to do, but all right, you haven't noticed any pause, but I've actually been looking for the answer to this question for a little while now, well, my previous work on the question, but for now, let's just kind of look at it. If we've got time going this way, and we've got an accelerating reference frame, say with acceleration g. G is usually given in meters per second squared. Let's say in rather than g in meters per second squared, but we need to put it in light seconds per second squared or something like that. So let's say we have 9.8 meters per second squared, and let's convert that into light seconds per second squared by converting 3 times 10 to the 8th meters in 1 light second. So this will be, whoops, that was silly. I gotta put this inverse because we want 3 times 10 to the 8th on the bottom, not the top. And that comes out to be 3.27 times 10 to the negative 8th light seconds per second. Actually, that's light seconds per second squared, not light seconds per second. Makes a big difference whether it's light seconds per second or light seconds per second squared. You cannot convert this to light years per year squared. Or, I mean, if you can, but you wouldn't get the same number. But you can write this d squared x dt squared is equal to 3.27 times 10 to the negative 8th, and light seconds per second squared. You could write, and moreover, you can write, overusing moreover, del squared x, let's call it rapidity. The rapidity of the object is changing at del t squared equals 3.27 times 10 to the negative 8th. And again, this will be light seconds per second squared. It's just that rapidity is kind of like angle. Actually, you know what? Instead of calling it light seconds per second, let's call it rapidians per second, because rapidian is kind of like a theta. So we'll use that. So now once we've got that set up, we draw this hyperbolic arc. And the hyperbolic arc is going to have a certain property. Let's get that property from Wikipedia. All right, characteristics of the Rindler frame. Scrolling down a little ways, we see this x equals c squared over alpha. All the Rindler observers are instantaneously at rest at time t equals 0 in the inertial frame. And at this time, a Rindler observer with proper acceleration alpha sub I will be at position x equals 1 over alpha sub I. Really, x equals c squared alpha sub I. Let's use that. X equals c squared over alpha sub I. And this alpha sub I is d squared x dt squared, or yeah, I wrote that wrong. This is, which is equal to delta change in rapidity over time. And it is c squared over the distance to the Rindler horizon, which is x. And so we're going to plug in, it'll be, well, let's solve it for x. X equals c squared over del phi del t, which is going to be c is 1 rapidian, No, 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 no. C is going to be infinite rapidians. Wait a second. Well, let's just brute force the math for now and figure out the units later. Okay, it's going to be 3 times 10 to the 8th light seconds per second squared divided by, and instead of using rapidians per second for this, we'll use light seconds per second squared for this. 3.27 times 10 to the negative 8th light seconds per second squared, which will end up with units of, I came up with 2.75 times 10 to the 24th, and that would come out in light seconds, but I don't like that answer because it doesn't look familiar to me. I was expecting it to come out to be something more like 10 to the 16th light seconds. The reason well, actually not 10 to the 16th, 3.1, somewhere around 3.15 times 10 to the 6th seconds, or no, 10 to the 7th. This is light seconds, which is approximately 1 light year. This is what I remember getting in this calculation before. So let me check. And just to be clear, it's not because there's any reason that it would come out to be 1 light year. It's just because that was what I remember it coming out to be when I've done the calculation before. So let's look at this again, 9.8 meters per second squared. We're going to multiply that. We're going to do 2 conversions this time. We'll do, you know what, let's do light years this time. There are 9.461 E15 meters per light year. 9.461 E15, and that is meters per light year. And then we'll take seconds. There are 31.5 million seconds in a year. So then I'll square that. And this comes out to be 1.03 light years per year squared. Okay, this is where the 1 came from. So I did remember something coming out to be 1 light year per year squared, but it wasn't the Rindler radius. It was just the 1.03. Wait, oh yeah. Wait a second. If this is coming out to be a different value than the other one, then there's some kind of misconcept. Let me look and see, what do we get? Okay, so let me check 9.8 meters per second squared and do it with the other conversion factor, which is, what is it? 1 light second is about 3 times 10 to the 8th meters per second. No, not meters per second, just meters. Because this should be how far a light second is. It's about 3 times 10 to the 8th. This is coming out to be 3, whoops, 3, 3.27 times 10 to the negative 8th light seconds per second squared. Okay, so this makes sense. This is 1.03 rapidians per year. This one is 3.27 times 10 to the negative 8th rapidians per second. So that totally makes sense. Those two do make sense. Now for the final part of this, x equals c squared over basically del change in rapidity over time. We can choose between the speed of light in time. Well, either way, we could write 1 light year per year squared divided by 1.03 rapidians per year. Basically, rapidian is a unitless sort of thing, and square that. And this gets me about 0.943 light years. Oh, this isn't squared. Okay, let me get rid of the square. This is not squared. This is 0.971 light years. All right, let's do it with the other format. We'll take c squared is 1 light second per second and divide that by 3.27 times 10 to 3.27 times 10 to the negative 8th rapidians per second. Again, not squared. And it comes out to be 3 point, wait, yeah, 3.06 times 10 to the 8th light seconds, which is just a little bit less than 3.15 times 10 to the 7th light seconds. 31, just a little bit less than the 31.5 million seconds in a year, which would be 1 light year. So yeah, they both come out to be about the same answer, with Rindler coordinates being approximately 1 light year. What did I do wrong up here? Man, x equals c squared. Oh, here's my error. C is 1. That's right, 1 light second per second, not 3 times 10 to the 8th. That's why this came out really bad. Okay, that makes more sense now. Sorry I didn't spend more time just yet on Stefano Quattrini's approach. I just want to get my own ducks in a row related to how, proper acceleration, which would be given in the delta rapidity, delta t. So 9.8 meters per second squared as g comes out to be 1.03 light years per year squared, or 3.27 times 10 to the negative 8th light seconds per second squared. Both of these, the 1.03 and the 3.27 times 10 to the negative 8th, can be expressed as a number of rapidians per year, and that is our proper acceleration. Sorry, 1.03 rapidians per year, or 3.27 times 10 to the negative 8th rapidians per second. But I'll have to break for there right now, because this thing sometimes has a tendency to mess up the video if I go for too long past 20 minutes, or if I include too many animations or something. Ta-ta for now.